Why would you want to know about the decibel? It's used in many fields such as audio production, broadcasting, communications, electronics, and audiology, just to name a few. The concept of the decibel is a bit different from most the units of measure with which we're accustomed. For example, we use inches to specify the length of an object, and we use pounds to specify weight. Working with electricity, we use the volt to measure the electrical potential between 2 points in a circuit, and we use the amp, or ampere, to measure current, which is the flow rate of charge between 2 points in a circuit. Power is measured in watts, and is the product of the voltage across the load and the current flowing through it. The decibel was created with power measurement in mind, but for the purpose of relative comparison, rather than the measure of absolute magnitude. A brief look back into the history of the decibel's development will help us to better understand its purpose and concept. In 1876, Alexander Graham Bell received a patent for the invention of the telephone, and shortly thereafter formed the Bell Telephone Company. Early telephones were very different from the phone you likely carry in your pocket today. For one thing, they were connected by copper wires, and the signal power came from the speaker's voice. As a signal travels along the line, it grows weaker, losing power as it is converted into heat by the cable's electrical resistance and other dissipating effects. In the days before signal amplifiers and digital carrier systems, line loss imposed a practical limit on the distance over which a telephone call could be possible. Bell technicians developed a practice of specifying signal loss in terms of cable length, but as the company's engineers and scientists worked to advance the technology, signal loss, and in the case of amplification, signal gain, were considerations applied to much more than cable. A more generalized standard was needed, and in the 1920s, the engineers and scientists at the recently formed Bell Laboratories conceived of the Bell, naming the new unit in honor of the inventor and company's founder. Note, however, that, unlike the inventor's name, the unit is spelled with one L, not two. The telephone engineers were first interested in loss caused by their long cables. But the decibel can quantify loss regardless of the cause. It is calculated as a comparison of the power delivered to the power from the source. When we connect a speaker to an audio signal source of sufficient strength, we can hear the signal as sound. However, if we then connect the speaker to the source through very long wires, the sound we hear will be reduced by loss. We can use decibels wherever we want to compare differences in power levels. Let's use a simple circuit to see how to do it. We have a signal source supplying power to a load, in this case a resistor. With only the single resistor connected, and no other loss-causing elements, we know that all of the power will be transferred from the source to the resistor. In other words, power from the source and power delivered to the load are equal. If we add another resistor to the circuit in series with the load, this resistor will now absorb a portion of the power supplied by the signal source, leaving a smaller portion of the power to be delivered to our load. This is similar to the loss caused by the very long cables. Let's represent these powers using subscripted variables, P-source, P-loss, and P-load. Intuitively, we know that the two resistors absorb all of the power supplied by the source. Therefore, we can write this relationship as loss power plus load power is equal to source power. It's easy to understand that the lost power is equal to the difference between the source power and the power that reaches the load. However, rather than simply keeping the loss as an arithmetic difference, decibels represent change, positive or negative, as a ratio, which we find by dividing the load power by the source power. Let's illustrate this using some numeric values. Imagine that our resistive divider reduced the power arriving to the load by half. If our source were delivering 2 milliwatts, our load would receive 1 milliwatt. The units of each of the two measurements cancel out. Since the load power is less than the source power, the ratio is less than 1. A ratio less than 1 represents a loss. Alternatively, a ratio greater than 1 would represent a gain. The next step is to find the base 10 logarithm of the ratio. At first, this might seem like unnecessary additional complexity. But logarithms offer some important advantages. One is that they can map a large range of numbers into a relatively smaller range. It acts as kind of a compression function. For example, the base 10 logarithm of 1 million is only 6. In the audio field, this is especially useful, as the human ear is capable of perceiving an extremely wide range of sound levels. The base 10 logarithm is usually written without the subscript 10, and this is probably how you will see the key for this function labeled on your calculator. Don't confuse it with logarithms of other bases, such as the natural logarithm, which is usually written as ln. When we're talking about bells and decibels, we are always using log base 10. In our example, we had a power ratio of 1/2 or 0.5. Taking the base 10 log of 0.5 gives us minus 0.3. The log of a number between 0 and 1 is always negative. The log of our ratio directly gives us our power relationship in bell. Use of the bell unit is now uncommon, as shortly after it was introduced, consensus settled on the smaller decibel as more practical. As the Greek prefix deci suggests, it is 1/10 the magnitude of the bell. The bell is abbreviated as an uppercase B, while the decibel is indicated by preceding this with a lowercase d. To convert from bell to decibel, multiply by 10. Now we can see that the ratio of 0.5 from our example is the equivalent of minus 3 dB. We can say that we have a loss of 3 dB, while thinking of the word loss as representing the minus sign in front of the number. To review, the formula to find the number of dB is 10 times the log of the ratio. If we plot the base 10 logarithm function on a graph, we see that y values slowly increase as x continues toward infinity, and continue infinitely negative as x approaches 0. Notice that for x values greater than 1, the logarithm produces only positive values. And for x values between 0 and 1, that is to say fractions, the logarithm produces only negative values. Keeping in mind that a ratio of less than 1 means a loss in power, and a ratio greater than 1 means an increase in power, we see this characteristic of the logarithm works very nicely to represent gains and losses with either negative or positive values. And what about the case where two powers are equal? That is to say, power entering a circuit block exits unchanged. It has neither experienced a loss or has been amplified. The ratio of two equal powers is 1. The log of 1 is 0. Multiplying by 10 results in still 0, and we will have 0 dB as a result. To review, negative decibels represent a loss. Positive decibels represent a gain, and 0 decibels represent no change. There is a pattern in the numbers worth noting. A ratio of 1 is 0 dB. 1 is equal to 10 raised to the power of 0. A ratio of 10 is 10 dB. 10 is equal to 10 raised to the power of 1. A ratio of 100 is 20 dB. 100 is equal to 10 raised to the power of 2. A ratio of 1000 is 30 dB. 1000 is equal to 10 raised to the power of 3. Maybe you've already spotted the pattern. The number of dB is 10 times the exponent to which 10 is raised to equal the ratio. It works for ratios less than 1 as well. A ratio of 1/10 is minus 10 dB. 1/10 is equal to 10 raised to the power of negative 1. A ratio of 1/100 is minus 20 dB. 1/100 is equal to 10 raised to the power of minus 2. A ratio of 1000 is minus 30 dB. 1000 is equal to 10 raised to the power of minus 3. Remember that the decibel was invented for the purpose of comparing power levels, and not to serve as a unit of measure representing an absolute quantity. However, decibels can be used to represent an absolute quantity of power, but as a ratio to a known reference quantity, and this is a common practice in many fields. The dBm is used to represent power levels relative to 1 milliwatt. The same can be done using the units dBW when referenced to 1 watt. Let's apply this using a typical example. Let's assume we have a radio transmitter that can provide 2 watts of RF power at its output. This is equivalent to 3 dBW. As another example, let's say we have a 30 milliwatt signal arriving on a transmission line. As the level is in milliwatts, it makes sense to represent the quantity in dBm. 30 milliwatts divided by 1 milliwatt gives us 30. Finding the log of 30 gives us approximately 1.5. Finally, multiplying this value by 10 gives us 15 dBm. Another advantage of logarithms is their product rule. It states that the logarithm of a product of two numbers is equal to the sum of the logarithms of each number. As an example, we have a signal source that can output 1 watt. We can increase that power by feeding that 1 watt signal into an amplifier. If the amplifier increases the signal power by a factor of 2, which is to say that the amplifier produces an output that is a replica of the input, but at twice the magnitude, then we know that the output of the amplifier will be an identical signal with a power of 2 watts. We know this because we multiplied the input of 1 watt by the amplification factor of 2. Remember, 1 watt can be represented as 0 dBW. How do we calculate that? 1 watt divided by 1 watt equals 1. The log of 1 is 0. 10 times 0 is 0. Therefore, 1 watt is 0 dBW. We know that a gain of 2 is equivalent to 3 dB. Let's remind ourselves how to calculate that. The log of a ratio of 2 is equivalent to 0.3. 10 times 0.3 equals 3. Therefore, a gain of 2 is equivalent to 3 dB. From the product rule of logarithms, we now know that adding the gain in dB to the power in dBW is the same as multiplying the power in watts by the amplification factor. Thanks to the product rule, all we need to do to find the resulting final power from the effect of gain or loss is add these to the power we start with. In this example, we add the 3 dB of gain to the 0 dBW of power we start with, and we find that after amplification we end up with a power of 3 dBW. As an example, consider a radio installation consisting of a 10-watt transmitter, a 12 dB gain amplifier, and 8 dB of cable loss to an antenna. You can check for yourself to verify that 10 watts is equal to 10 dBW. How can we calculate the amount of power to the antenna? To our power level of 10 dBW, we add our 12 dB gain and subtract our 8 dB of cable loss to arrive at 14 dBW. This example should demonstrate the clear advantage of using decibels for signal level analysis. To verify our answer, let's go through it the long way. 10 dBW is the same as 10 watts. The gain multiple of the amplifier is calculated by dividing the number of dB by 10 and raising it to the power of 10. That gives us a multiple of 15.9, which means that the output of the amplifier will be 15.9 times the input power of 10 watts. 159 watts are sent into the cable from the amplifier. However, the power reaching the end of the cable will be all that power divided by the cable loss factor. 8 dB of loss is equivalent to a loss factor of 6.3. Divide the 159 watts by 6.3. We are left with 25.2 watts at the antenna, which is equivalent to 14 dBW. We can calculate the power into a load by knowing both the voltage across the load and the impedance of the load. This is due to the relationship between voltage, impedance, and power, where power is equal to the square of the voltage divided by the impedance. Finding the ratio and expressing it in decibels is straightforward. If Z1 and Z2 are equal, as they often are within a system, we can dispense with them, as they will divide out, and the equation simplifies to a ratio of the squares of the voltages. Further, the ratio of the squares is equal to the square of the ratios. This brings us to another interesting characteristic of logarithms, which is the exponent rule. The logarithm of a number raised to some power is equal to the logarithm of that number multiplied by the power. Knowing this rule, we understand that the log of the square of the ratio of voltages is equal to 2 times the log of the ratio. To find the number of decibels, we multiply 20 times the log of the ratio of voltages. For this to be valid, it is necessary that the impedances across which the voltages are measured be the same. Here's a simple example. Let's say that we have an audio signal generator driving a loudspeaker. Initially, the voltage amplitude of the signal is 1 volt RMS. We'll call this V1. We then increase the output level of the generator to drive the loudspeaker with a signal amplitude of 3 volts RMS. We'll call this V2. The impedance of the loudspeaker is the same before and after the increase in signal amplitude. We can calculate the increase in power of the signal to the loudspeaker based on the increase in amplitude of the signal. However, we must keep in mind that power varies with the square of voltage. To calculate dB from a voltage change, we must multiply the log of the ratio by 20 rather than 10. The ratio of voltages is 3. The log of 3 is approximately 0.477. Multiplying 20 by 0.477 gives us 9.54 dB. As previously stated, the decibel was created with power in mind. However, you have likely seen other apparently related units referring to voltage, such as dBV or dB micro V. In similar fashion to how decibels are used to represent an absolute quantity of power, they can also be used to represent an absolute quantity of voltage. The dBV is used to represent a voltage relative to 1 volt. Again, this is only meaningful in systems where the impedance is constant. This is also a common practice at milli and microvolt levels, where the dB milli and dB microvolt units are used. Since 1 volt is equal to 1000 millivolts, we can easily convert from dBV to dB millivolts by adding 60 dB. To convert the other way, from dB millivolts to dBV, we subtract 60 dB. If you are new to using decibels, they can be confusing at first, and it's easy to get tripped up. But with a little practice, you'll quickly become fluent in their use. We hope that you found this video useful and informative. If you did, please hit the like button. We plan to produce more videos in the future that we hope you will find useful. So, please subscribe, and let us know about any other subjects you would like to see videos about. We value your feedback, and leaving it in the comments section will help us make better ones in the future. Thank you for watching.